Universidade Estadual do Norte Fluminense, being Rio. Today, we will deliver mathematical modeling of one-dimensional oil displacement by combining solvent-thermal flooding. Please, Adolfo.
Thank you, Eduardo. First, I would like to congratulate Professor Dan for his birthday and for his brilliant career. And tell something, I met Dan first time a few years ago, when I was taking my PhD with Pavel Bedrikovic, and he was collaborating here with Dan and Professor Bruining too. And we came here for those workshops in PGEs in the end of the 90s. And it was very interesting for me because I'm an engineer, so it's to be in touch with this more fundamental math, and it was a great incentive to keep studying these hyperbolic systems and Riemann problems. And okay, I try to learn a little bit. Maybe you'll see something today. And this work is conducted by me and Tamiris. She was a master's student, and now she's beginning her PhD. So it's just some exploratory analysis of this combined flooding in EOR process. And I will present a few slides showing some physical aspects, some oil production aspects of enhanced oil recovery. Then we'll go through the physical and mathematical model and this first example of solution and some remarks and mainly what we are planning to do in the next few years. Okay. So why use enhanced oil recovery? The idea of enhanced oil recovery is try to produce that difficult oil. And enhanced oil recovery maybe it's the only way to produce some oil like very, very viscous, highly viscous oil using thermal methods. And I can say that this is the most important method of enhanced oil recovery because of the heavy oil. But in the last few years, because of the greenhouse gas sequestration, CO2 sequestration, the miscible flooding is improving its importance in the point of view of the production based on enhanced oil recovery. So besides thermal, that the name says is that the injection of addition of heat to the reservoir to try to decrease the oil viscosity and allow it to flow. The chemical methods is the addition of some chemical components to the water, to the injected water, so it changes its mobility in the reservoir. And the most known problem, let's say, especially here in the mathematical point of view, is the polymer injection. Polymer flooding is changing its viscosity, and that gives rise to those structures for the Riemann problem that I use some of them to show our solution here. And as I said, miscible flooding is also becoming important because of the mass transfer. Let's say the use of CO2 as a gas to be injected, or even at the use of solvents like propane, ethane in steam injection. It's mass transfer, mass exchange between the injected fluid and the reservoir fluid leads to improvement or a better viscosity, a better flow of the oil in the reservoir. So what motivates us to analyze these, let's say, combined enhanced oil recoveries? Because in recent years, or let's say at least 10 years, people in lab have found some nice results, some important results when they combine, as I said, steam with solvents, ethane, propane or something. And also what's the idea is to combine the addition of heat with some enhancement because of the mass transfer. So what I'm going to present here is the hot carbonated water flooding. So the idea here is to combine the advantage of water flooding with carbon dioxide, thinking about the two good points. That is the mass exchange, carbon dioxide being dissolved in oil. It will decrease its viscosity, allowing enhancing its flow capacity, and also the carbon dioxide sequestration. And the heat is also improves because of the viscosity. So what's interesting is that when we were analyzing the system of equations, we noticed that it was very similar to other problems evaluated, or analyzed also, like solvent with steam and hot carbonated water flooding. From the mathematical point of view, the system of equations is exactly the same. And depending on the physical properties, depending on the physical constants that, let's say, that lead the process of mass transfer between phases, and even how do you see the how do you work, how do you evaluate the thermodynamic equilibrium between gas and liquid, or between liquids, as we are going to show here. What we are proposing, what we are planning to analyze is if it changes the wave structure and if some of the waves goes faster or slower in the porous media. This is an ongoing work. So we begin with the mass conservation of each component, and here each component is oil, solvent, and water, but specifically in this problem we are talking about solvent as carbon dioxide, and the phases are oil and water. As I said, if we change water by gas and also the solvent for any solvent, we have exactly the steam with solvent injection. And of course, the energy conservation. Here capital U is the internal energy, and capital H the enthalpy of the phase. And ρ is the density, S saturation, and here C is the mass fraction of component I in phase J. Okay? Of course, all those hypotheses, so we can be allowed to solve something. We consider only one-dimensional flow. We try to split the effects of the physics. In a homogeneous and isotropic porous medium, we neglect diffusion, gravity, and capillary effects. We consider the system incompressible, and we also consider that Amagas law is valid, so we can move from mass concentration to volume concentration. The enthalpies are functions of temperature, constant heat capacity, and the pure component density is the same in both phases. Here, for liquids, it's a reasonable assumption. When you work with gases and liquids, maybe it's not so good hypothesis. Here is a simple sketch. We consider the displacement of oil, and in oil phase there is only oil and solvent, and the liquid phase there is water plus solvent, in this case CO2. We consider also that there is no oil in the water phase and no water in oil phase. So we have, from the thermodynamic point of view, 4 unknowns: the concentration of the solvent in water and the oil phases. Of course, as the sum must be 1, we must solve only 2 concentrations. But we have to choose any thermodynamic model. And here is something that I'm presenting one choice, the first choice, but it's our idea to see how the thermodynamic model impacts the results, if it does. We consider that the Henry's law is valid, so the concentration of the solvent in both phases are related by 2 constants. That in fact is only 1, right? But as we want to write something for liquid and liquid gas, if we have the gas phase, we can replace it by partial pressure. In fact, what we do here is the equality of the fugacities, here by using Henry's law. So we have a linear relation between the solvent concentration, the CO2 concentration in oil and water phases. So it's the simplest one. And through Amagas law and the constant density in all phases, we can move from mass concentration to volume concentration. Of course, we also consider the L as the characteristic dimension of the our porous media. We have dimensionless position and dimensionless time as the number of pore volumes injected. So after we apply these considerations, we get this. What did I do? It's okay. We get this components conservation as a function of the volumetric concentrations and the relations of the Amaury's constant. If we deal with solvent with steam injection, here we have a relation between Amaury's constant and system pressure. Also, it will have an impact on the, we believe that there is an impact, we still don't know. And oil, solvent, water, and the energy conservation. Here, MT, as is our constants, is the component density and the specific heat capacity at constant pressure of the components and the rock. So we have 4 equations, but we don't need to solve. Yes?
Your original energy was, so you threw away the you just.
Yes, we do not consider the kinetic energy. Right. Another hypothesis, I forgot. Thank you. And so these are constants. And so we have 4 equations, but we have only 3 unknowns because all the concentrations are related through the restrictions, auxiliary relations of the sum of concentrations that sum up to 1, also the saturations sum up to 1, and the fractional flow. As usual, the fractional flow is defined as the relation between the phase velocity, here we chose the oil phase, and the total velocity of the system, of the fluids, of the phase, liquid oil and liquid water. So we chose as unknowns the oil saturation, the CO2 saturation, CO2 concentration in oil phase, and temperature. So the final system in matrix form, and then we have 3 eigenvalues, hyperbolic system, and what we found that this structure, this hyperbolic system, is very similar to the polymer or chemical flooding, and also the temperature, the hot water flooding, the steam injection with some considerations. So we have the 3 eigenvalues. The first one we call the saturation wave, where only oil saturation changes. The second one we call the concentration wave, where temperature is constant and both saturation and concentration changes, is similar to polymer flooding, miscible flooding also, and it's controlled by the mass exchange. And the third one that we call energy wave or temperature wave is similar to the solution of a 2x2 system when there is temperature and saturation evolution. And here just showing the first family rarefaction to the saturation. The saturation and concentration we see in both families, temperature is constant. And the third family, it's a linearly degenerate wave. So this gave us the idea, also the Rankine-Hugoniot conditions, the shock conditions. After some manipulation, it's possible to show that we have 3 kinds of shock. Temperature shock, where saturation also jumps, Buckley-Leverett type shock, and also concentration shock similar to the problem of polymer and miscible flooding. So after studying these problems, getting some papers of Professor Dan, Professor Han, Amaury, and others here, we saw that we had a similar system of equations and similar structures for the case of polymer injection, for steam flooding with solvent nitrogen. And then we postulate that we could solve this problem in a similar fashion. Let's say we have the left condition, and then we solve like a Buckley-Leverett problem with some chemical dissolvent until we have the coinciding waves that also appears here, at least for the parameters that we analyzed. Then we have the concentration transition. For this case, was a rarefaction. And from the right condition, we also have saturation, rarefaction, and a Buckley-Leverett type shock. Of course, it depends on the position of the temperature shock. So for this problem, we found that the temperature shock, the energy shock, it lies exactly, not exactly, but in the right part of the solution. So we have the general solution for these parameters, the saturation rarefaction, then the concentration rarefaction, and then another saturation rarefaction, the temperature shock for this problem, another saturation rarefaction, and then the Buckley-Leverett. So we found the solution for this set of parameters. So all of them are usual, but what I would like to point out is this relation of the Amaury constant. Okay, we use some experimental data to get these relations, and the usual we have a water injection with some CO2 dissolved, a classical relative permeability solution, right? And we just chose zero residual saturation just for simplicity, but there could be any residual saturation. And these are the models that we chose for viscosity, oil viscosity as a function of the CO2. You see that it doesn't change much for this case. Water viscosity. For the oil viscosity, that's the importance that I would like to stress, that for the oil viscosity, that there is an impact on the fractional flow function. We have the effects of the CO2 concentration and also temperature, right? Okay. It's not absolutely unclear how to see, but there are three fractional flow functions. But just to stress, I will present some zoom of these regions. There is here from J to A, the saturation rarefaction. From A to B, the concentration. Is this part here, is a zoom. Here, the point A is the coinciding wave speeds, coincident speeds of both waves, saturation and concentration. From A to B, we go from the injection conditions to the intermediate conditions, where there is a concentration rarefaction. For this case, of course, if we change the concentrations, a shock may appear. And then here at B, another constant state. And then we have, here you see, we have the saturation rarefaction. The concentration rarefaction is green. It's also not so clear. A constant state, a saturation rarefaction here. And then the temperature shock, the jump here. Another constant state, then from the intermediate fractional flow function curve to the initial fractional flow curve, then the classical Buckley-Leverett solution. Because of the position of the temperature shock, we have a rarefaction and a Buckley-Leverett type shock. In another position, of course, we could have only two shocks and two constant states. So this is the profiles for the solution for this particular case. Here from J to A, saturation rarefaction, concentration rarefaction is not clear, constant state, another saturation rarefaction, temperature jump, constant state, saturation, and the final Buckley-Leverett type shock. Just a zoom, because here it looks like, no, it's okay. For the concentration, rarefaction, and temperature jump. and the solution in the phase space from J to A, the only saturation change, saturation concentration, and then the other saturation change, the temperature shock, and here the Buckley-Leverage shock. So some remarks and some comments, because this is an ongoing work. We could find, based on our postulation, that we could split the problem, Hibban problem, in two parts, and let's say, and include the temperature shock in the correct position. But we could solve this problem of oil displaced by hot carbonated water. And it's a similar solution for steam injection with solvents, but we have a lot of work to do. So we need to test or try other thermodynamic models, not this simple one, and not only for liquid-liquid equilibrium, but also for gas-liquid equilibrium. And besides that, when we consider steam injection, consider another phase, the third phase, because we have only, let's say, vapor and oil. If we can include water condensation, so another phase, and then I don't know if we can find some approximate solution in some condition. I have no idea, but it's something that we plan to evaluate. And also, I believe that this, seeing your presentation yesterday, I had some ideas that maybe we can try a compositional model for a simple equilibrium and include not only CO2, but more than one component, and try to find some equilibrium relations that allow us to split that system into, let's say, auxiliary system, and then solve this system only for the phase equilibrium conditions, and then solve the general model, the general problem. So these are, let's say, we did almost nothing compared to what we plan to do, but first steps are given. I believe that I have some ideas of what to do from here on. And I would like to thank also there is some financial support from research projects funded by Petrobras, and CAPES and UENV for scholarships for some students. And Dan told me that he speaks Portuguese, so feliz aniversário. And thank you.
We have time for 1 or 2 questions, please. Please.
So there is no combustion involved?
No. No combustion, just.
How far away is that? Can you accommodate that also?
I don't know, I'm not sure, because I can't say now, because we have a source term. Just the source may be solved, but I don't know how to write all these pieces. I don't know. Maybe it's a good suggestion, it's here. Yes?
A silly question. What is Amagat's law?
Okay. They say the Amagat's law is similar like pressure, like you have ideal gas. Sum of the partial pressures is total pressure. The Amagat's law is the sum of partial volumes is the total volume, ideal solution. So the partial volume of each component, you sum up, it is the total volume.
Who uses this terminology or this?
Amagat's law?
Yeah.
And chemical engineering is classical.
Yeah?
Yes.
Okay. Thank you.
But usually you have that partial molar volumes are a function of the concentration.
Yes.
And then it is almost as simple as Amagat's law, I guess.
Yes.
Okay.
It's ideal solution.
And the variable C hat SO is exactly
It's volumetric fraction. Without the hat is the mass fraction, and then with the hat is the volume fraction.
okay.
So you are in Macaé, right? So
Yes.
how seriously Petrobras take those ideas and apply?
Okay. No, it's the thermal.
General, just
No, enhanced oil recovery, they are considering more. And also there is, we are beginning to discuss let's say, application of this theory, not only this application of this theory, is that we are is something that I have been working for a while with some students. Is a streamline simulator. We have the 1D solution, but now we are discussing with my colleague Alvarez and some people in Petrobras is apply part of this theory combined with compressible system, considering, let's say, the virgin zone, the oil zone, as compressible classical diffusivity equation, to use it in well test pressure transient analysis. So try to understand the pressure behavior in the wellbore with time for transient period, to evaluate the feasibility of this EOR in long terms. It's still something that we are beginning for the years to come.
So, let's thank our speaker again, please.
Thank you.